A quick recap on harmonic identities. You might be given exam questions like this one here, where you are given a trigonometric expression like this and asked to put in this form. You're pretty much not going to be given this part here. Typically, you'd normally have to work out. They won't give you a range for it. It's normally the first value you get from your calculator. Typically, they want you put in this form so that later on you can solve these equations down here for the given range over here. Now, if you're given this expression in the first place, and then it came to this equation here, and in terms of attempting to solve that, if you try to use traditional methods writing out the equation, it might be trying to balance it out, but then it's hard to get your cos and sine to one ratio here. 8 is getting in the way. Here, you might say, you know what, I can replace it because I can use my trig identity, my sine squared theta plus my cos squared theta is equal to 1. Therefore, I can say in this situation that sine squared theta is equal to 1 minus cos squared theta. Therefore, sine theta is equal to the square root of 1 minus cos squared theta, and that you can substitute in here. But as you can see, as we continue this manipulation steps, it actually just gets more and more complicated still. So here is that substitution expanded, just taking out, it's multiplying out 12. Here we are subtracting 5 cos theta from both sides, dividing both sides by 12, squaring both sides, and then it comes into this quadratic expression, which is quite complex to solve. So let's go through the actual steps in the question here using that form. So arranging for the r cos alpha form, you just need to expand this from your compound angle identities. You get this. I've now highlighted this and brought back my original expression from the question. So this part here, beg your pardon, this part here is just rewritten down here so we can see it, and so we can compare with our expansion from our compound angle identity here. So when we're looking at these two, I can see it's exactly the same expression, both containing cos thetas and sine thetas, and I can see being multiplied by my cos theta is r cos alpha. So r cos alpha, which is here, must be equal to 5, and here multiplied by sine theta is r sine alpha. So r sine alpha must be equal to 12. So I've written those two things down here, that r sine alpha is 12 and r cos alpha is equal to 5. We know that tan is sine theta over cos theta, so we can write these on top of each other, recognizing that two r's are just going to cancel out. I'm just left with sine alpha over cos alpha, which is just 12/15. I can now use arc sine to work out the angle represented, and I'll put this into my memory, my calculate memory for exact answer. The question here just wanted 2 decimal places for the value of a, so that's fine. Then we are going to find a value for r. We ask for r for two decimal places. We recognize that I can square each of these values, so I can square r sine alpha and square r cos alpha, and it should be equivalent to 12 squared plus 5 squared. Doing so, I end up with these, and these being squared. I can factor out r and get this. So r must be equal to 169. Therefore, the square root of that, r must be 13. The next part of the question says find the maximum value of 5 cos theta plus 12 sine theta, and the smallest positive value for theta for which it occurs. Okay, so the maximum value is going to be the highest point on the curve, because that has been stretched from 1 times 13, so we get a maximum value here of 13, and then the smallest value of theta, so that's going to be the lowest value in this, and we know the graph shifted. Normally cos starts off where 0 is here, that's where 1 is, but the graphs have been shifted to right by 67.38 degrees. Therefore, that is the smallest value of theta for which it occurs. We know it's going to repeat at the next maximum, the next local maximum again, but 67.38 is the lowest value for which this maximum occurs. The next part is actually solving this. So as we said before, we can't solve it when it is in this form here, but we do have it in this form where it's a single ratio, it's just in cos. So whilst it's in cos, I can substitute my 13, which I know, and my 37.38, which I know. You can use exact values for greater accuracy. I know that my original limits were this, between 0 and 360 degrees. Taking into account my transformation, I'm going to say this is now going to go from minus 67.38 to 292.68 degrees. And I can see the shift down here represented on the graph. And using a calculator, you can very quickly see where these points intersect. There's going to be 2 points of intersection within range and one which is beyond the range of values. And very easy to use your calculator and your GSolve button to double check what those are.